do you have, you had tutorial yesterday? Okay, so I think I have a few minutes. So, okay, so before I start, is the dinner timing and the bus okay, or you want to have dinner a little bit late and, late? So what time was the dinner yesterday? 6. So what time you want? 7? 6:30? Huh? How many for 7? Okay. How many for 6:30? Okay. Okay. How many for 6? Okay. Okay. So maybe we'll just do around 6:45 or something, so that it makes everybody happy. And bus was what, 7:30, right? 7:45. So is it okay if bus leaves at 8 o'clock? You can also have two buses, one leaving at 7:45, another leaving at 8 o'clock, right? Right? So how many for 8 o'clock? Okay. And 7:45? Yeah, very few, because the problem is that if everybody, all of you come to the 8 o'clock bus, and then 7:45 if it is, yeah. So maybe, okay, depending on if you guys come, 7:45, if one bus is full, it will leave, and then the next bus will be full as 8 o'clock. Yeah. Okay. So, so do you have any questions from last class? Okay. So if not, so let me just, okay, so this, so I realized that I was not giving a title for the course, so let me just make it basic properties of okay. So although I said stochastic processes yesterday, it's too broad title, and I mean, because I have only 3 lectures, most of the time I'll be actually spending on Brownian motion. So let me make this title a bit more specific. Okay. So let me just recap what we did yesterday. So we basically wrote down the Langevin equation for Brownian motion, right? So which is, so the full Langevin equation which we wrote down is this is equal to f of x minus gamma v, plus we also found out this coefficient from equipartition, and so this was the equation, right? So we said that this eta is a noise, so we call it a white noise with mean 0, and it's uncorrelated in time. So the correlation is a delta function. Okay. So it means that at any t not equal to t prime, this is 0, and at t equal to t prime, you can think of it this delta function as basically 1 over the delta t, where delta t is basically your discretization time step. Okay. Okay. So these are the only properties we use. Okay. So later I am going to use actually eta, I'll just call it a Gaussian random variable. So okay, with mean 0 and variance is given by this, and again if you just think of it in the discrete time delta t, so variance goes like 1 over delta t. Okay. So we said that there is a time scale tau which is m by gamma, and if you are sampling this system at a time scale which is larger than this m by gamma, okay. So did you calculate this number yesterday? Okay, so you should calculate this, okay. So as I say, it's I mean, depending on what value we put, it should get something between 10 to 100 nanosecond, okay. So if you are sampling it at larger scale, so if you divide by this gamma, so then you can forget about this term, okay. So this is called the overdamp limit. So what we get is the overdamp equation, and which is basically given by, now I replace v by dx dt. So, what I have is dx dt is 1 by gamma f of x plus square root of 2d times eta of t. Eta is the same eta, and then d is just kbt by gamma. Okay. So, normally when you call Brownian motion, okay, you generically actually mean this equation. In fact, you most of the time when you call a Brownian motion, you actually mean the equation without f equal to 0. Okay. And this equation, now you can think of this, d is some parameter of the problem basically, right? You can forget about this, okay, this, okay, what we are doing in some particle in the water or something, okay. So, let us just look at this case when your f of x is 0. So, you have a equation, so dx dt is equal to square root of 2d times eta of t, right. So, where eta has the same property, and d now you can just think of it as some parameter, okay. It's just a diffusion coefficient, but it need not be in general, okay, this is for, okay, some particle in water or something like that, right, okay, there is some temperature adjusting, okay. But generically you can just define this model, and this is what is called Brownian motion, and it's not only applicable for, let's say, particle in water, but it has various applications, right. I mean, any, so this is basically, I guess, one can think of it like a most fundamental stochastic process basically, like this is like the 0th order stochastic process, okay. So, when you think of a stochastic process, this is the first model you are going to try basically, okay. And so, we saw that, okay, there is a Fokker-Planck equation corresponding to this model. So, okay, for this one what we saw is that, okay, the Fokker-Planck equation is given by this, okay, and so this is the case f equal to 0, and then what we find is that this p of xt is given by minus infinity to plus infinity dx0 p0 of x0. So, this is the initial distribution at time t equal to 0. So, this I give you, okay. So, it can be either delta function when you always start with at one point, but in general this can be some distribution times g of xt given x0 0, and this z xt given x0 0, this is given by 1 by square root of 4 pi dt exponential minus x minus x0 whole square by 4 dt, right. So, this is the Gaussian propagator we have, right. So, this is what we did yesterday, okay. We also wrote down the Fokker-Planck equation corresponding to this one, okay, but this, as I said, that that Fokker-Planck equation look quite different from the Fokker-Planck equation for this problem, and okay, you require usually if you want to go from there to there, so you actually it involves lot of steps, intermediate steps. So, I am not going to go through it today, okay. Yeah. Yes. There is no velocity. No, in the sense that, I mean, you can think velocity is random in some sense, okay. dx dt, if you just think of it as like a velocity, it's like a random. So, point is that you have this guy. So, if I divide this equation by gamma, right, so I divide it by gamma, so I have 1 by gamma and kbt by gamma. So, I have this equation. So, now, so this gives me a time scale tau, right. So, this is what my tau is. So, now imagine that, okay, you are looking at the system under a microscope, okay, this is some number. So, as I said, this number if you compute for 1 micron particle in water, I mean it's depending on the density, it's somewhere between 10 to 100 nanosecond, right. Now, suppose you are just looking at this under the microscope. You can, your microscope can, whatever, your camera can only record, let's say, at 1 microsecond, right? It cannot go record at 1 nanosecond. Okay. So if your camera is recording at 1 nanosecond, and if you want to describe that motion, you need this equation, right? But suppose your camera is recording at 1 microsecond, okay, which is much larger than this time, right? So now, so what are you doing? You are looking at this trajectory of this particle, okay, at 1 microsecond apart. So this is some discrete jump, right? Okay. So now that trajectory, if you want to describe, okay, to describe that trajectory, because within that 1 microsecond, so forget about all these other terms. So what is the damping term for the velocity? Damping term from the velocity comes from this and this guy, right? And that guy, if I just take this equal to this one, I know the solution. So goes like V of t goes like whatever V of t plus delta t. If I just solve this term and this term, I just only take this term. So what we will see is that V of t plus delta t is V of t exponential of minus delta t by tau, right? I am not taking any of these terms, right? I am looking how this velocity is damping, right? So this one, if delta t is much larger than tau, right? So this term is going to go to 0, right? So it means that basically, of course, now there is fluctuation because of all these terms, but this inertial effect that the velocity it had at time t, basically time delta t before, right? It does not remember that velocity. Okay? So in other sense, velocity equilibrates at that time scale. Okay? So now if you want to describe your motion, okay, at a time scale beyond this tau, okay, so you do not have to take into account of these velocities. Okay? So velocity in some sense becomes a random variable, right? Okay? Only non-zero velocity is coming from the randomness, okay, because it does not remember its previous velocity, whatever it was, right? So then in that limit you can forget about this term, right? Or in some sense you are basically taking this term is going to 0, right? Because in that term this is not very important compared to all the other terms when you want to describe your motion at this time scale. Okay. So that is your overdamp limit. So if I just put this term equal to 0 and then I just put this velocity to this side and just write as dx dt, which is my this equation is. Okay. And that equation, okay, so yesterday we solved that, okay, when we had f equal to 0, so we saw that this is the solution. Okay. So now if we have a case where f of x is not equal to 0, okay. So we also wrote down the equation for that case. So what was the equation? So we had the equation del p del t is equal to minus del x fx by gamma p plus d del 2p del x square. So this is the equation, okay. So in general, of course, this equation is very hard to solve. You cannot even solve for all f of x, right? Okay. So now we want to see whether we can say something about this model, okay, some properties. So let's say, okay, so let us assume that case where f of x is derived from a potential, right? So f of x is minus u prime x, right? Minus du dx, okay? Okay. So it's only a function of x minus du dx. Okay, so we are going to assume that. And let's assume that u is a confining potential, Okay, so confining potential means that, okay, u, if I put u of x, okay, so this goes to infinity as x goes to infinity, okay, in a certain way. So we are going to see what are the requirements, okay. So at this point, okay, so we say that, okay, it goes to infinity, u of x goes to infinity as x goes to infinity, okay, in a certain way, okay, such that it confines the particle within the potential. So we'll see what are the requirements, how it should go to infinity, okay. But let's for the time being assume that, okay, it's sufficiently confining this potential that it confines the particle within this thing, okay. So if it confines the particle within that, so what's going to happen? So this system, after some time, this p, which is a function of x and t, right? This p is a function of x and t, right? As t goes to infinity at very large time, this will be only a function of x, okay? Okay? So its system will reach a steady state, okay? And we want to find out what is this steady state, okay? So we are saying that as t going to infinity, we are saying that p of xt goes to some p steady state of x, okay? It becomes independent of t. And what is this p of x? We want to find out, okay, for f of x, which is given by this. So how do you find out? So in that case, since it is only a function of x, so left hand side is going to be 0, and right hand side, what do we have? So this guy, I'm going to put minus u prime x, okay, so that minus minus plus, so I have plus. Now see, there is a del del x acting on that, and there are two derivatives. So in fact, I can just take one derivative out of the full thing, right? So I can write del del x of u prime x by gamma plus d del p del x. In fact, this becomes a dp dx now, because p, sorry, this is u prime x by gamma, p, which we are calling p stationary, which is just a function of x, plus d dp stationary by dx, which is a function of x, right? So this is what we have. So now this left hand side is 0, okay. That means that this guy is a constant, okay. So if it's a constant, okay, so it's same everywhere, okay. So let's say what is this function at infinity, okay. So we are saying that, okay, this we have a potential which confines this particle, therefore we cannot find any particle at infinity. So therefore both of these guys should vanish at infinity. So therefore this thing should be 0 at infinity, but since it is a constant, it should be 0 everywhere, right? So therefore this constant is equal to 0. So this is a constant of space, right? Because space is the only this thing. So now I look at what is this constant at infinity. At infinity, I said that, okay, I have a sufficiently confining potential, right? There cannot be any particle at infinity. Therefore, Px is what? Probability of finding a particle between x and x plus dx. So this should be infinity, 0. X going to infinity, right? Because this is a function of the space. I look at x going to infinity, okay? So at x going to infinity, there cannot be any particle, right? So therefore, this thing should be equal to 0, and also this should be equal to 0, right? So in fact, what is this guy? So if you look at the negative of this guy, So minus d del p dx, it's actually a diffusive current. Okay, so it's just the current. Okay, so if you look at a Fick's law, so Fick's law has the current. So minus d del p del x. So that's the diffusive current. Okay, and minus of this guy is basically the drift current, right? Because minus of this is force, minus of this guy is the force by gamma. So force by gamma is the V terminal, right? It's the terminal velocity times I am multiplying by the probability. So therefore, when I multiply the terminal velocity times the probability, is like multiplying the terminal velocity by the density, right? So this is the drift current. This times, so if you multiply this by P, so this is the minus of this, okay? No, plus of this is drift current, but F is minus of it, right? So therefore, if I take the minus of this is the total current, okay? So it says that total current is constant, and that total current is 0 at infinity. Therefore, the total current should be 0 everywhere. Okay? Yeah, at t tends to infinity. So we have a sufficiently confining potential, and t tends to infinity, we have a stationary state. The distribution does not depend on time. Okay. So now we are saying that, okay, that gives me this condition. That means the inside is a constant. So now if I look at this, this is a constant in space, right? There is no time here. So now I look at this at x going to infinity. Okay. So I said that at x equal to infinity, this has to be 0. And since it is a constant, it has to be 0 everywhere. Right? So now, if it is, derivative is also 0. If there is no particle there, everything is 0, basically, right? So as I said, this guy, you can also, this is also the negative of this is also the total current, and total current has a part which is the diffusive part, right? Because what is the diffusing current? So if you imagine that you have a lot of particle here, right? You spray some perfume here. After some time, you are going to smell it, right? Because there is some current from the high density to the low density, right? And it goes from high density to low density. That's why this is the negative gradient. And the proportionally constant is the diffusion coefficient, right? So this is a diffusive current. Similarly, if you have a force, okay, force will drag this particle. It reaches a terminal velocity. Terminal velocity is F by gamma times this density, which is the probability density here, is the drift current. Right? Because current is number of particles going through a per unit surface per unit time, right? So it says velocity times the density, basically, right? Okay. So therefore, if I just add this together, so this is basically negative of that. So which is the total current? Okay, and total current has to be 0 at infinity, because if there is a current at infinity, of course there will be a particle, right? So if I say that there is no particle at infinity, there is no current also at infinity. So now if we put this, so I have an equation which is just the inside is equal to 0, but this is an equation you can solve, right? So you have an equation dp steady state by dx is equal to, I'll put this thing here, so minus u prime x by gamma d times p steady state, right? And you know the solution of this equation. Right? I can take p here, dx there, and I can just integrate this one. Right? So solution is that p steady state x, okay, there's some constant, okay, times exponential of the integral of this guy, right? So which is exponential of minus, if I take integrate this one, so I get u of x by gamma of t. Okay, and gamma of d, gamma times d is same as somewhere I have written kbt, right. So this is equal to exponential of minus u of x by kbt. And what is this constant? Because it is a probability density function, if I integrate over all space, it has to be equal to 1. So therefore, this one, if I integrate this guy, so that has to cancel with this guy. So this constant is e to the power minus u of x by kbt dx. So total current is 0 is a consequence that the steady state is an equilibrium state, right? So you can have a steady state where you have a current, right? But that state need not be an equilibrium state, right? So you can have a constant current, okay, and still you can have a time independent state, right? So steady state means that your state is independent of time. But in this case, since this current is 0, so whatever the steady state we got, it is also an equilibrium state, right? And we recognize this guy, right? So what is the denominator? It's just the partition function, right? And this is basically the Boltzmann distribution, no, or Gibbs distribution, right? So the system is, so this is the equilibrium distribution of the particle. It says basically it equilibrates to a temperature T, okay. You see that gamma completely disappears from the problem, although we had a gamma there, right? Because, so D had a gamma, right? So although we had a gamma, it completely disappears from the problem because your equilibrium state does not depend on gamma, right? It only depends on the temperature. Right? Yeah.
So my question is like regarding how can we know that there is a steady state which is like.
So we are assuming that so now we are going to see how do you know that there is a steady state. So we are assuming that we have a potential confining enough, okay, so that basically it confines this particle. So there is a steady, if there is a confinement, okay, the system cannot evolve indefinitely, right?
But in principle, even at a confining potential, the particle could have sort of gone back and forth.
So there is damping in this problem, right? So it cannot keep oscillating. This kind of motion is not allowed, right? There is a damping in the system, right? So if there is no damping, of course, things can go back and forth.
In the overdamped case, I don't see the damping term. That's why.
This is a damping term, no? This is a damping term. This is a damping term. You still have a gamma. But you still have gamma.
Yeah.
Gamma means damping, right? Gamma still appears in that equation, right? Okay. And so I'll see actually later how, okay. So I'll come back maybe either today at some point, or if I cannot do, I'll do it tomorrow. So why do you assume that there is a stationary state, right? Okay, so today just now what I said, okay, based on some intuition, right? So let's say a little bit more concrete, and we see why there is a stationary state, okay? So before doing that,
So can this expression is true for any form of U prime of
this, so that's what we are going to see now, okay? So we are saying that, okay, assuming that there is a stationary state, assuming that I have a U for which I have a stationary state, okay? Assuming that I have a stationary state, this stationary state is given by this, okay? So now can I take any form of U where this expression is true, okay? So that means what I have to see whether this integral, does it converge for any U, okay? So we need to look at the partition function, right? Okay. So what is the partition function I have? So I have this integral exponential of minus beta u of x is 1 by k bt, I just call it beta dx, okay, minus infinity to plus infinity. Okay. So, if there is a stationary state, I need this to converge, right. So, what kind of potential that does gives me this conversion? Okay. So, so this integral, of course, okay, there is no problem near x equal to 0. Okay. So, any divergence can come only from x going to infinity, plus infinity or minus infinity. So, just like let's look at, let's say, the plus infinity side. Okay. So, it's the same. Okay. So, suppose if you have a ux which goes like x x to the power alpha as x goes to infinity, right. Similarly, x goes to minus infinity, you have a similar form, right. It can be x to the power minus x to the power beta or something like that, right. It need not be the same alpha and beta on both sides, right. So, you can have, let's say, some minus x to the power beta as x goes to minus infinity, right. But let's just look at on one side, because if we understand on one side, it's the same, right. So, this integral, so you have an integral now like e to the power minus beta x to the power alpha dx infinity to from some lower limit, because the lower limit really doesn't matter. I am just interested in the convergence or divergence of this integral. Does this integral converge? So, in fact, this integral converges for all alpha greater than 0. Okay. So, any positive alpha, this integral converges. Okay. So, if you have a potential which increases as a some which increases algebraically, right, x to the power alpha both sides, this is going to converge, right. So, I am coming. So, therefore, any potential even which increases faster than this definitely going to converge, right. So, x to the power alpha, or even if it is increases exponentially, it will be exponential of exponential, it will be made converges like that. So, this is going to converge, right. Okay. You have a question?
Yeah, it should be at least as fast as algebraic.
Yeah. So, now let us see what happen when alpha going to 0 limit, right. So, alpha going to 0 limit is in some sense it goes logarithmically, it is still an increasing function, right. So, this case of course it converges, right. Okay. So, this guy is some cutoff, I am just doing this integral from something, right. So, now let us look at the case u of x goes like log x as x goes to infinity, right. So, let me just call a log x, okay, there is some power and it goes to infinity, right, because this still it increases, right. So, this is the, after this is the slower one. So, what is this integral now? This integral will be, so if I look at this integral exponential of minus beta u x dx some lambda to infinity. So, this integral goes like some lambda to infinity exponential of minus beta a log x beta a log x dx, right. Beta a I can take it inside, and then exponential of log x to the power beta minus log x to the power beta. So, that comes down. So, this, can you see down? Is it visible here? Okay. So, this becomes something like lambda to infinity 1 by x to the power beta a dx, right. So, does this integral converge or not? I am looking at a large, so this is a large X behavior, right? So beta A should be greater than 1, right? So beta, if beta A is equal to 1, it's going to diverge logarithmically, okay? And if it is less than 1, of course, it's going to diverge as some x to the power something, right? So therefore, beta A should be greater than 1, right? So that gives me a constraint that if I have a potential like that, okay, so then A should be greater than, so what I have is, so maybe let me just write it somewhere there. Okay, let me just write it somewhere there. So what we have is that beta A should be greater than 1, it means A should be greater than 1 over beta, or A should be greater than KBT, right? So therefore, any algebraically increasing potential or faster increasing potential is going to confine the particle, okay. So borderline case is when it increases logarithmically. So in that case, it depends on the prefactor, okay, and if prefactor is greater than KBT, right, so then it's going to converge. So KBT does what? Its temperature tries to push things away, right? So in this case, there is some kind of competition between temperature trying to push things away versus this potential trying to pull things together, and it basically appears like that, okay. So if A is less than KBT, it's not going to confine, okay. So therefore, when I say that, okay, sufficiently confining potential, so I mean that this potential when x goes to infinity or minus infinity should increase at least as fast as A log S, where A is greater than KBT. It can of course increase faster, right. So all those potentials, so you will have a stationary state, okay. Okay. So next we are going to come back to still, okay, why do we have a stationary state, okay. I mean that's still an intuition, right. I am saying that, okay, some confining potential is going to confine this particle, okay, this thing. But now let us see more mathematically why we should expect a stationary state. So we will start with this equation, but we will start with the case where f of x is derived from a potential, okay. So let us just write down there, okay. So I am going to leave some intermediate steps, and I expect you to do it in the tutorial. So who are the people doing tutorial? There are some students, no? You are there, yeah? Huh? Okay, yeah, okay. So all these intermediate steps, okay, you first try to do it yourself, and if there is any confusion, just these are just simple algebra, okay. So let's take the case where f of x is minus u prime x, right. So this is the case, okay. So what is the Fokker-Planck equation? So Fokker-Planck equation is del p del t is equal to del x of u prime x by gamma p plus d del p del x square, okay. Okay, so let's skip this thing. So now, so this we can in fact write it as a, we can also write this guy as a, so let me just write it here, so that, so this we can also write it as a del p del t is some operator acting on p, some differential operator. So what is this operator? Del x u prime x by gamma plus d del 2 x2, right. So this is the Fokker-Planck operator. Okay. So in principle, okay, formally I can solve this equation. So what is the formal solution? Formal solution is basically that P of xt is exponential of L T P of x0, right? This is just a formal solution. Okay. But okay, is this operator Hermitian? Right? So how do you find a operator which is Hermitian or not Hermitian? So you find the, so what is the definition of a Hermitian operator? The adjoint of the operator has to be equal to this. So the operator has to be self-adjoint. Okay. So how do you define an adjoint of an operator, differential operator? So you define by saying that it's a differential operator x on x space. We say that dx. So if you have two functions, let's say psi of x, L chi of x, this is equal to dx chi x L, right? It's in some sense this operator when it acts on the left side, that's the adjoint, right? So if you just think of it like a matrix, okay, okay. So if we think, okay, this guy is in some sense like a matrix product, okay. So in some sense, this guy you can think of is like a some matrix, and some matrix, right? So if this matrix, okay, this is some L matrix, this is of course a continuous space, but okay, just think of it like an infinite dimensional matrix. So when this guy works on this is this operator, but when this guy works on this other side, that's just the adjoint in some sense, right? So it's acting on the other side, right? So this one, now if you have an operator del del x, so it has two parts, one is this part and one is this part, right? So let's say what is this part? This part is Hermitian or not? That you know it's Hermitian, right? How do you know? Huh? Because you know something from your quantum mechanics, right? But how do you show that it's a Hermitian operator? You just do this one, right? So how do you do? So if you have this guy, so dx psi of x, this guy is, okay, del chi of x. Now you integrate by parts, right? And you assume that these functions and its derivative, they vanishes at infinity. So if you integrate by parts 1, so this gives me the boundary term vanishes, then the minus. So what is this? Dx, the derivative of this, integral of this. So derivative of this is psi prime x, integral of this is one derivative psi chi prime x, right? So now you do one more time. So that gives me minus minus plus, okay, integral dx, you differentiate this guy, psi double prime x chi x, right? So this guy is, okay, it's just a function, it doesn't matter which order we write. So this guy becomes dx chi x del 2 del x2 psi of x. This I am also writing like a partial, but these are just the ddx basically, right? Because it's just a, if it is just only a function of x, right? But I am putting it there, okay, if there is some parent, okay? So you see that this guy, this is this form, right? This is the same operator, right? I started with this operator acting on chi on right side, psi is there, I got back the same operator. So therefore, this part is Hermitian, right? Because that's what you get, no? In quantum mechanics, the kinetic energy term is okay minus a squared by 2 1 d2 dx2. So that's a Hermitian part. Okay. So what about this other part? So let's just go do the other part now. So what is this other part? Del del x u prime x by gamma. See, this gamma is not important. I can actually take it out because it's not a function of x. But okay, let's just skip it. So this guy. So now let's do this calculation again. This guy gives me del del x u prime x by gamma chi of x, right? This is what it means, right? This is operator x on the right hand side. I do by parts, okay? So when I do by parts, it gives me minus dx psi prime x. I integrate this guy, so that gives me u prime x by gamma chi of x. So now let's write down in this form dx chi, I want to put it under this side, chi of x, and then okay, let's just put this minus side inside. Okay, so what I have is minus u prime x by gamma, just a function, I can write it in any order, right? Psi prime x, so which is del del psi del del x acting on psi of x, right? So now you see that this guy, we started with this operator, right? So you can just think of it, this acting on chi x, right? So this acting on this guy, chi of x, right? So this operator, we started with this operator, we ended up with a different operator. This operator is not same as that operator, right? So therefore, if I look at the adjoint of this operator, so what we have is this guy comes outside and there is a minus sign. So minus u prime x by gamma del del x plus d del 2 del x2. Okay. So this operator is not a self-adjoint operator. Okay. So it's not a Hermitian operator. So it has consequences in the sense that we know that if I have a Hermitian operator, the right eigenfunction and the left eigenfunction are complex conjugate of each other, right? So that's why in the quantum mechanics we have psi star psi, right? One is complex on the other, right? So in this case, that's not the case. Okay. So now we still okay. So one does not have to do that, but okay, since you guys know much more about quantum mechanics because immediately you say that this is a Hermitian operator because you know from quantum mechanics. Okay. So let's see this equation. If I can cast in form of some quantum mechanics, right? You know some equation in quantum mechanics, right? So what is the equation in quantum mechanics? You know. Schrodinger equation. So what is the Schrodinger equation? The Schrodinger equation, I h cross del psi del t, but since I am also using a t here, let me just distinguish this t and just put a q subscript just to say that okay, that t subscript I just putting is just to indicate that this is this quantum time in the quantum mechanics problem I am looking at, right? It's just some variable. I can call it tau or something, but I just put this tq so that I know that I am doing the quantum mechanics, right? So this is what? This is equal to h psi, but I am going to write this h in this form. So what is h? minus h cross square by 2m del 2 del x2 plus v of x, and the whole thing x on psi, right, which is a function of space and time, right. Psi is here, psi is there, it's just there. Okay. So this guy is my Hamiltonian. Okay. So I just take the minus psi on this side. Okay. And then you look at that this, okay, minus I can put minus I down. So this side I can write del psi del I by h cross dq. Okay, I just put it inside, it doesn't matter, these are constants, right, is equal to, so I have taken out a minus sign, so this equal to h cross square by 2m del 2 del x2 minus v of x psi of xt. So this guy is just minus h basically.
So, sir, this psi will be a function of TQ, or
It's a function of tq, sorry. My t is tq, it's just a this thing. So it's a function of tq. Okay. So that side, whenever I say t, it will be tq. Okay. So if you notice that I put this q, you will this thing. So you see that this equation has some similarity to this equation, but not exactly, right. So what are the difference? Okay. So it has a second term. So this term is there. If I just okay. So if I identify this t, so if I identify this t as I by h cross tq, okay, and d as h cross square by 2m, okay. So I have an equation. So what is this equation? I have an equation del psi del t is equal to d del 2 del x2 minus v of x psi of xt. Now it become t because I just gone from t to this thing, right. I mean you can put tq equal to I by this thing t, but okay, just think that it's just another function t, right. It's a function of t. It just says that it's a function of x and t. Okay, okay. Of course, you solve this one and this one. It's not that putting tq equal to t. Okay, putting tq equal to actually this guy. Okay, so this equation and that equation. Okay, so this guy is still minus h, right? So what is the, what did you do? So you look at the quantum mechanics problem, okay, in imaginary time, right? That's just a mathematical this thing, right? So you are looking at the quantum mechanics problem and taking time to infinity. Tq we are taking to be minus I h cross t basically. So you are taking time to be imaginary. Okay, you are looking at that. Okay, so this time going from the real time to imaginary time. Okay, this is called weak rotation. Okay, it's just a rotation in the complex plane of the time. Okay, so this is just there is nothing fundamental about looking at this quantum mechanics in infinite time. It's just a mathematical transformation, right? Don't think of your quantum mechanics particle moving in some imaginary time, right? So when you're right, so now okay, so we are going to go this, but this solution already you see that it's now psi of xt is exponential of this minus ht psi of x0. right? The consequence of making this transformation is that earlier it would have been by I h cross h t, so this guy goes away, okay? Okay. So now why did I do this? Okay. So I have one equation of this and I have another equation this. Okay. Are these two equations same? So what is the difference between this equation and that equation? So this guy, so if we look at this guy, so this equation if I look at, okay, right hand side, so let's expand this right hand side. Okay. So what is this right hand side? So one guy is of course u prime x by gamma del p del x plus u double prime x by gamma p. Okay, that term is same. So you have a derivative term in this problem. Okay, in fact this is the term which is making it non-Hermitian, right? We know that this quantum Hamiltonian is Hermitian, right? So we want to do a transformation, basically going from this problem to that problem. Okay. So how do we do? We need to somehow get rid of this term, right? So what we are going to do? So we are going to do no, v of x we do not know yet.
I mean, or some function of.
Yeah, so we do not know what is v of x, right? We said that we want to get this equation to that form, right? So v of x we don't know, that's the potential in the quantum mechanics. My potential is u of x, right? So I don't know what is that potential. Okay. So what I am going to do, let's try, okay, if it works. So what I am going to do, we are going to use p of xt. So I am going to assume, okay, I am going to assume it's a function of some f of phi of x, I do not know, times psi of xt. Okay. So I am going to assume this, and I am going to put it, substitute this in this equation. Okay. So this equation, call it 1. This, okay, this is 1a, which is basically the part of this thing, and this equation, let's call it 2. So when you substitute in 1, okay, you see that left hand side will have phi del psi del t, right? So that phi you can take it to the right hand side, it will be like 1 over phi, then whatever this thing. So you can make left hand side to be del psi del t, right? Okay. This term, this is a double derivative term. Okay. So there will be one term. So how do you get a double derivative in psi? So you take this guy and you are, so this guy when you take derivative, you have to take derivative this, keeping this thing, then derivative that, keeping this in, right? But there will be one term where you keep this term out and double derivative of this term. Okay. So there you are going to get one term which is d del 2 psi del x2. Phi is outside, but then you have a divided by phi, and of course this, yeah, so that phi is gone. So you are going to get one term like that. Okay. So you are also going to get some term, okay, 1 by phi of x, okay, because you have divided by phi, okay. See, when you do this derivative, because you have various derivatives, right, even there is term coming from this guy will generate a term which is derivative in phi, right, okay. So you are going to get some terms which are So this you will get some term which are del psi del x. Inside there will be some functions of phi, okay, some derivatives of phi and so on. Okay. So this is something you have to do. Okay. Then finally you are going to get a term which is proportional to psi, right? Because if you do like this, there is one term you can already see that, okay, u double prime p. So if you put it there, there is of course this becomes phi times psi, right? There might be also term coming from this guy. When you do phi times psi, there will be a term where psi will be coming outside and you will take a derivative of phi, right? So there will be term like that. So therefore you will get some term like this, right? And phi is your arbitrary function. Okay. So now you choose your phi. So what is your aim? So your aim is to get rid of this term. Okay. So you set this is to 0. Okay. So that will give you an equation for phi. Okay. And that determines phi. So you choose phi such that this term is 0. Okay. This guy also phi is there. You will then put the solution there, right? So this guy will give me a phi which says that phi of x is exponential of minus u of x by 2 gamma d. Okay. It almost looks like the Boltzmann distribution, but with a factor of half. Okay. So this is something you have to do. Okay. And then you will get this term. So in other words, so what I am saying is that, okay, now since I know the answer, so if I put p of xt is exponential of minus u of x by 2 gamma d times psi of xt, then this psi is going to satisfy the Schrodinger equation, which is given by this. Okay, so this psi is going to satisfy this equation. Okay, is equal to d del 2 del x2 psi minus Vx of psi of xt with this potential, because this potential we have to identify, right? With the potential V of x, which is u prime x whole square by 4 gamma square d minus u double prime x by 2 gamma. Okay, let me see if it is the case. I think that's probably the case. Yeah. Okay, I have got it right. Okay, so this is the potential. This is the potential. This is the quantum potential. Okay, you get corresponding to your destiny, right? So now, when do you have a stationary state when do you have a bound state in quantum mechanics? Okay, so we know that if we have a confining potential, we have discrete spectrum, right? And this discrete spectrum means what? So I have written down this guy. So it means that if my u of x is such that, okay, if my u of x is such that whatever the quantum potential I generate, that's a confining potential which has discrete spectrum. Okay, so then psi xt I can write as n equal to 0 to infinity some Cn. Okay, basically I am expanding this in eigenbasis. I am just putting a set of eigenbasis within this thing. Okay, times exponential of minus en t times some psi n of x. Okay, so I'll have this. Okay. So these are the ENs are the eigenvalues, eigenenergies, and these are the eigenfunctions. Okay. So therefore P of xt, which is exponential of minus ux by 2 gamma d n equal to 0 to infinity Cn e to the power minus Ent sin of x. Okay.
And all these science are actually real, right? Because we are doing it for probability.
Say it again.
Science are real functions.
Psi n's are just the eigenfunctions of this. So this is your Hamiltonian, which is minus h is so h is minus d del 2 del x2 plus v of x. These are the eigenfunctions of this Hamiltonian. Whatever the Hamiltonian is, that's the eigenfunction of that quantum Hamiltonian. The same, right? Right. So now, so P of x is this. So suppose you start with a initial condition at, because we still need to determine this guys, right? So we suppose start with a initial condition that at x equal to 0, your particle is at some position x, right? So let's assume that P of x0 is delta of x minus x0. Okay. So therefore, if I put t equal to 0 here, so that solution is what we call this green function, right? Basically starting from a delta function we go. So if you put x equal to 0, so what we have is delta x minus x0 is equal to e to the power minus, so let me just this equal to, but this guy I can just take it to the other side. So exponential of ux by 2 gamma d is equal to n equal to 0 to infinity Cn psi n of x. But psi n we know the orthonormality this thing, psi n psi m star. So what we have is that psi n x psi m star x dx is delta mn, right? So therefore, if I multiply by the psi m star and then integrate this, I get c. So it says that c of m is just, so when you multiply this guy, so this guy will give me exponential of minus, so what I am multiplying? I am multiplying by, okay, so this guy gives me exponential of u of x0 by 2 gamma d times psi m star of x0, right? So I multiply by psi m x integrating over x. So this guy gives me delta mn, so it's only m equal to n term contributes. That side, when I do integral over x, only x equal to x0 term survives. So x equal to x0 and psi m x0. Okay. So therefore, if I put it there, so what I have is, maybe let me just put it here. Maybe let's just put it here. So this P I will write it as a G because I just solve it for a fixed this thing, so that I'll just say that it's just a green function. So I say that G of xt given x0 at 0, this is, so there is this guy, so that comes out of the summation. So this term exponential of minus ux minus ux0 divided by 2 gamma d n equal to 0 to infinity psi star n x0 psi n x e to the power minus t. Okay, and this guy is what? This is just the quantum propagator, right, in this rotated time, right. So, this is my z, let us put quantum xt x0 0, okay. So, which is nothing but basically x e to the power minus ht x0, okay. So, in fact, this I could have just done it from here basically in some sense, right, because this guy I could have written it in this form, and then by doing all this initial and this condition I could have just written it down there, okay. So, now so let us just do an example, okay. So, there is some properties of En, okay. If this guy is a confining potential, if my classical potential is a confining potential, this En should satisfy some properties, this En should satisfy some properties. So, what is this En? Okay. So, these properties are basically that okay. So, one of the property it should satisfy is, so let us take an example, okay, where we know this Ens. So, which is a problem you know Ens? Harmonic oscillator, right, quantum harmonic oscillator, right. So, let us take an example. So, I think we have here this one, we can remove it. So, let us write it this case with harmonic oscillator. Okay. So, let us take the harmonic oscillator. So, let us take the classical case, say half lambda x square, right. This is the basically a particle in a harmonic potential. This is just a classical Brownian particle in a harmonic potential, okay. We go through all these steps, okay. So, we finally arrive at this one, okay. So, what is the V of x? So, V of x is this. So, let us compute V of x. So, V of x is u prime square. So, u prime is lambda x. So, this is lambda square x square by 4 gamma square d, that is the first term. What is the second term? If we took two derivatives, lambda minus lambda by 2 gamma, yeah, lambda by 2 gamma, okay. So, this part is in the classical harmonic oscillator. This is half m omega square x square, right. So, therefore, if you want to identify your variable in terms of this, so what do you get? So, we have basically m omega square is lambda square by 2 gamma square d, right. We have one more identification somewhere, which is h cross square by 2m is d, right? So h cross square by 2m is d. So in fact, if you multiply this side and this side, so what do you get? You multiply this guy, m cancels. So h cross omega whole square, 2 cancels, is equal to lambda by gamma whole square, or h cross omega is lambda by gamma. Okay. So what is the energy for this harmonic oscillator? N plus half h cross omega, but now we have a something, so minus, what is this? Lambda by omega is h cross lambda by gamma, so half h cross omega. So therefore this harmonic oscillator problem has an energy which is n h cross omega, where n is 0, 1 and so on, right? So what does it mean? So what does it mean? This one, let's just skip it. So what does it mean? So if you do this problem, so what does it mean? Okay, so what are the wave functions of this quantum harmonic oscillator? So Hermite polynomial into Gaussian, right? So psi of xt is some hn of some alpha x exponential of minus x square by something, right? So these factors, let's see if I have these factors. Okay, so what are these Hermite? Okay, yeah, times something. Okay, so okay, psi n of x is, there's something here. So I'll not write down the thing, so you can look it up. I have the thing here, but okay, it is not going to do any this thing. But only thing is that this Gaussian thing is same everywhere, right? So we are going to find out what is this Gaussian thing. Okay, I can actually put that thing. Maybe let's just put the thing. Okay, so that so let me just put the thing. So Hn of m omega by pi is close to 4. So let me just put the whole thing. Okay. So okay. 1 by square root of 2 to the power n by n factorial m omega by pi h cross to the power 1/4, then exponential of minus m omega by 2 h cross m omega by 2 h cross x square hn of square root of m omega by h cross square root of m omega by h cross times x. Okay, this is something you can just look it up. Okay, so it's not important at this point what are these things are. Okay, so now I am just interested in looking at this because I know that h0 is 1. Okay, and okay, if you put n equal to 0, all these guys are 1. Okay, so this is something. Okay, so now let's look at this term. Okay. So, this has, what is the lowest energy? It is 0. Okay. And what are the other energies? This is some, basically this is n h cross omega, right. So, what happens when t goes to infinity? So, only the 0 energy contributes, right. All the other terms goes to 0. Okay. So, this is just one example I have demonstrated. So, in all problems where you have a stationary state in the classical problem, so your ground state energy in the quantum problem has to be equal to 0. Okay. So, in some sense this, okay, so this energy has to be equal to 0. So, the ground state energy is 0, okay, because otherwise you cannot have a stationary state. Okay. So, it cannot be negative, right, because then your probability this guy is going to, yeah. In the quantum mechanics it is okay because these are oscillatory functions, right. So, whenever you have a break into eigenfunctions like that, the E0, so that is because you can only do that when you have a discrete energy spectrum. In that case, the E0 has to be equal to 0. The ground state energy has to be equal to 0. Okay. Okay, that's required. Okay. So, now look at the case. So, what happened when this, when we look at this case, all right. So, we have this one. So, we look at t going to infinity. So, you look at this object. Okay. So, what do we get? So, we look at the harmonic oscillator. So, e to the power minus 1 by 2 gamma d. Let us keep it gamma d because all this h cross omega we are going to actually convert into the our parameters, right. Ux, this thing, see, this is half lambda x square minus half lambda x0 square, right. This term is coming from this one. Okay. So, this guy is, okay, let me just rub this guy. So, this guy I am saying that only the 0 term contributes. So, this is psi 0 star of x0 psi 0 of x. This guy is gone. So, what is psi 0 of x? So, you look at this guy. So, this guy, right. So, let us just convert to our problem. Okay. So, this thing, let me just remove it now. Okay. So, let me convert to our problem. So, what is psi 0 of x? So, psi 0 of x is, all this thing is gone, only this one, exponential of minus m omega by h cross, no. So, we need this h cross by m omega, right. So, what is h cross by m omega? We know this guy, so we need h cross by m omega. So, if we divide this guy, no, we take this guy and divide this guy. Huh? So, let us see what do you get. So, this is basically h cross square by 2m, no, let's see. So, if we take h cross square by, so if we take this guy, so this guy is h cross square by 2m, so this guy gives me d on this side, then I am going to divide this guy. So, I am going to divide this guy, means m omega square here, right, and this guy I am going to divide. So, if I divide this guy, 2 gamma square d goes lambda square here, right. So, this is basically square, this guy 2 goes there. So, what do I have? H cross by m omega is what? 2 gamma by lambda. Huh? D can right? Is it correct? Okay. So let's just put it there. So we have x square divided by lambda goes up 2 gamma t. Okay. So now let's put it there. So how do you get? So if you put it there, okay. So there is of course this normalizations. Okay, these normalizations are coming from this guy, right? So this guy is still there is this normalization. So you'll see that actually it will be exactly the same normalization, right? Because this is pi h cross by m omega. So this will come to the normalization later. So you see that psi is this. So this is same as this guy, right? Right? So this guy gives me exponential of minus lambda x square by gamma d, right? Because this half and that half. So sorry, did I do something? There should be no. Sorry, what did I do? There's an extra 2 here, right? Sorry. X square by h cross 2 omega, there is an extra 2 there. That 2 gives me this 2. Right? So this guy got me this 4, but that 4, I also have a 4 from there. They combine, they give me this. But what happened to this other term? There is also this psi 0. Psi 0 also this guy, but that cancels this guy. Right? And you know that your stationary state cannot depend on the initial condition. Right? This is a state when you are taking t going to infinity that cannot remember x0. Okay? So now this guy, so this is whatever this state now. Okay, so this state is different from your that state psi. So this is the eigenfunction of your this operator L. Okay, this is the lowest eigenfunction of this operator L. Okay, which is slightly different from this guy. And this operator basically should have the property that if you have a confining potential, if there is a bound state, this operator should have the property that the lowest highest eigenvalue is 0 and all the eigenvalues are negative, right? So that all the other terms decay. The eigenfunction correspond to the zeroth eigenvalue, the right eigenfunction correspond to the eigenvalue is given by the stationary state. So that stationary state, what we had said earlier, we said that okay, we just assume of this thing, right? So that corresponds to the eigenfunction of this operator, which corresponds to the zeroth eigenvalue. And there is another eigenfunction on the left side, right? Which is the eigenfunction of this L again. So what is that eigenfunction? That eigenfunction is 1, right? Unlike in this problem, even at n equal to 0, you have both left and right, right? Here the other one is just 1. Okay, so this is a generic property of these processes, okay, like this Markov operator. So it's actually it's true for both discrete time and continuous time. I think obviously it's going to tell it at some point. Okay, discrete space. Okay, so this corresponds in the discrete space. So you have a matrix now, right? So the left column vector is all elements are 1. Okay, so in this case, this is the case. Okay, okay. So this is of course not necessary to go through this step. We could have, in fact, if you wanted to solve this harmonic oscillator problem, I could have actually solved this problem directly. Okay, it's equally easy or equally difficult, right? Okay, I mean, this I did not actually solve the problem. No, I just read it off from whatever I know from my quantum mechanics class, right? But if you want to solve this problem, you have to solve this differential equation and go on like that, right? So you'll have a similar method. So you don't need to go through this whatever transformation, but this is one intuitive way to see basically that, okay, why when you have a stationary state and when not, and when you have a stationary state, basically when you have a this guy. So you can see actually if you have a log potential, what happens. Okay. So in the quantum mechanics problems, sometimes what you might have it actually, you might have a single bound state, right? You might have a single bound state and then a continuum of state, right? If a delta function and something, you have a single bound state and then you have a discrete spectrum, right? So even if you have a single bound state which is separated by this continuum, you still have a ground state basically. Okay, so that's the only requirement basically for having this stationary state in this problem, right? So this one, so we'll come back to this problem tomorrow. So tomorrow I can do two things. Okay. So today, okay. So I want you to go through this thing today. So tomorrow, since it's the last lecture, so I can talk about two things. So which one do you want me to talk about? So first thing I can talk about the path integral formulation of this Brownian motion. So that's one option. And second option I can talk about is basically look at this problem, and this is a free problem I was doing either with potential or without potential. But now we might ask, okay, I mean there are some problems called first passes problems. Basically you might want to ask, okay, if I start from somewhere and this particle moves, right? So let me just write it here. So imagine that you have this particle either with potential or without potential. Okay, you have this particle, and imagine that you have some target here at x equal to 0, and you're starting with some x equal to, starting from some position x equal to x0, right? So this particle is moving, and at some point, okay, it's going to hit this target. Okay, so this you can generalize it to, okay, starting from any position x0, and your target is at some point a, let's say. So this guy is moving, at some point it's hitting the target. Okay, so this is a target hitting problem. So you can find out what is the time at which it hits the target. Okay, this time will be a random variable, right? Next time you look at, so this guy, okay, will come, probably it hits at this time. Okay, next time again you start from the same thing, okay, you come and it hits this time. So this is a random variable. So this time is called the first passes time. So it's basically coming to that for the first time. Okay, and it has a distribution. Okay, so you can ask questions about, okay, these properties of this kind of problems. Okay, you can ask, okay, so this is related to, you can also ask, okay, there is some thing, let's say there is a bomb at x equal to 0, and you are moving something and you want to avoid this. Okay, imagine that there is a rat trap there, and the rat is doing a Brownian motion. And whenever it just comes and it just hits the thing, it dies, right? So how long it survives? Okay. So you ask what is the probability that at time t it actually does not hit this object, right? This is something called survival probability. Okay. And how do you determine this survival probability or first passes kind of problems? Okay. So either I can do that or I can do the similar thing but in a path integral formulation. Okay. So which one should I do? Huh? Huh? First passes? Okay. Path integral, first passes. How many for path integral? Okay. Huh? How many for first passes? Okay, there are a lot of people who have first passes. And how many people have path integral? Okay. So maybe, okay, so what I'll do, so I'll do, okay, I'll try to probably do both. Okay, 9:30 to maybe 45 minutes I'll do one, and 45 minutes I'll do other. That means that I am going to leave lot of steps, and that you will have to do in your tutorial. Okay. So I am not most of the algebra I will just skip it. Okay. So you just have to do it in the tutorial, right? Okay. So maybe I will start with the path integral when it becomes 9:30 to what 10:15. Exactly at 10:15 somebody stops me, and then I will go to the other problem and I will do the other one. Okay. Yeah.
Here we are assuming that this solution
Ah.
of Schrodinger equation
Ah.
works both for real and imaginary time, right?
Yeah.